It is one of the most powerful magnets in the world. Its magnetic force is so intense that it can crush any object trapped between them. But how are neodymium magnets made? We visited the largest rare earth deposit in the world and a magnet factory to discover how neodymium is extracted from nature and how it is transformed into one of the most powerful magnets on the planet. Neodymium is a metallic element that was discovered by Austrian chemist Karl Auer von Welsbach in 1885. But it wasn't until the second half of the 20th century that its true potential was revealed. Scientists developed a new type of rare earth magnet. They discovered that, when combined with iron and boron, neodymium could form incredibly strong magnets, much stronger than conventional ferrite magnets, and lighter and more compact. Ideal for miniaturizing devices, this discovery revolutionized the tech industry and gave rise to essential components in electric motors, wind turbines, and electronic devices. To obtain neodymium, tons of rock are extracted from open-pit mines in Bayan Obo, northern China, a region known for hosting one of the largest rare earth deposits on the planet. From these minerals, neodymium is carefully separated, a metal fundamental to the manufacture of powerful magnets. This mine is one of the largest sources of neodymium in the world. The minerals that contain it, such as bastnasite and monazite, are embedded in formations rich in rare earth oxides. To extract them, large drills are used, capable of making a series of deep and precise holes in the rock. These holes are used to place explosives that will fragment the rock. Once the explosives are placed, blasting is carried out. This technique allows hard rock to be broken into more manageable fragments, making subsequent extraction easier. After blasting, the fragmented rock is loaded by excavators and mechanical shovels into large haul trucks. These vehicles transport the material from the blast zone to the processing plant. Once the rock arrives at the processing plant, a series of complex chemical treatments begin to isolate the neodymium from other rare earth elements and impurities. At the plant, the rock is crushed into smaller particles to release the minerals containing neodymium and other rare earth elements. Then, they are separated and classified by size to facilitate chemical treatment. The mineral undergoes a leaching process where it is mixed with acids such as sulfuric acid. This action dissolves the rare earth oxides, including neodymium, forming an aqueous solution that contains dissolved ions. The resulting solution contains a mixture of several rare earth elements with very similar chemical properties. To separate them, a technique called solvent extraction is used. An organic solvent is added that selectively extracts certain ions. Through multiple stages of contact and washing between the aqueous and organic phases, the different elements are separated one by one. The separated neodymium in solution precipitates as an insoluble compound, typically neodymium hydroxide, by adding a base such as ammonium hydroxide. The precipitated hydroxide is then filtered and dried. The dry hydroxide is heated to high temperatures to transform it into neodymium oxide, a stable powder that is easier to handle for industrial use. Neodymium is concentrated into a fine powder with a metallic gray hue. This powder is carefully poured into 200-liter steel drums. A worker taps the edge of the drum to loosen any residual powder stuck to the inner walls. As an additional safety measure, they secure a steel ring to seal the container. The drum is labeled with the content information, weight, and purity level of the neodymium. Next, the drums are transported to a specialized plant for producing super powerful rare earth magnets. To manufacture the magnets, the first step is to create a sand mold in the desired shape. A special tray is used that forms 4 cavities, one for each magnet. This tray is placed into a machine that completely covers it with sand. Once removed, the surface is slightly uneven due to the pressure of the machine's lid, so it is manually smoothed to ensure a uniform mold. Then, the tray is returned to the machine, which this time injects special gases that chemically harden the sand. The solidification process is fast and lasts just a few seconds. At the end, a hardened sand block is removed that contains the precise imprint of the magnet models. That block is now considered a functional mold. Magnets come in many shapes and sizes, and so do the molds. Each one is specifically designed according to the type of magnet to be produced. Now, they are ready to shape the magnets. The second essential step is producing the alloy powder of neodymium, iron, and boron. the base of neodymium magnets. All these materials are stored in controlled atmospheres under inert gas to prevent oxidation, especially neodymium, which is highly reactive with air. Next, the three elements are introduced into an electric induction furnace. Approximately 30% neodymium, 2% boron, and the rest iron. The furnace generates a pulsing electromagnetic field that reaches temperatures above 1600 degrees Celsius and melts the metals uniformly. To prevent the neodymium from reacting with oxygen, it is kept under vacuum. Once melted and homogeneous, the alloy is poured into sand molds. As the molten alloy is poured, it completely fills the mold cavity, reproducing every detail of the design. The molds catch fire, since the gases that harden the sand are highly flammable. After pouring, the molten alloy is left to cool inside the mold. The burning molds are transported to another section of the foundry and dumped onto the floor. During this solidification process, the metal contracts slightly, which is why molds are usually designed with tolerances to compensate for this contraction. Cooling must be controlled to avoid internal stress, cracks, or warping. An external cooling system is used to speed up the process without compromising the metal's structural quality. Once the metal is fully solidified, demolding begins. Then the sand mold is broken to release the metal piece. This piece is a neodymium iron-boron block in the raw shape of the magnet, but still without magnetic properties and without coating. The neodymium iron-boron alloy rings undergo heat treatment to improve their internal structure and prepare the material for magnetization. First, the rings are placed into a heat-resistant metal tube, which is completely filled with silica sand. This sand serves two purposes. It holds the rings firmly in place during heating and evenly distributes the temperature. Once the tube is filled, both ends are sealed with refractory cement to prevent oxygen from entering and to protect the contents during the process. Then, the tube is placed inside an electric furnace, where it is heated to temperatures generally between 900 and 1100 degrees Celsius until the rings glow red hot. This heat treatment improves the material's microstructure, removes internal stresses, and gets it ready for magnetic alignment. Although the rings are now solid and have their final shape, they are still not magnets. The next step is magnetic alignment. A strong and constant magnetic field is applied while they are still hot. This field aligns the material's internal magnetic domains, the small regions that determine the direction of magnetism. At this point, the rings become slightly magnetized, but more importantly, their internal structure is correctly oriented to receive final magnetization. Then, the seal is removed from the tube, and the rings are carefully extracted. Now, they pass through a machine that applies a powerful magnetic field pulse, up to 3 Teslas. This pulse activates and permanently fixes the domain orientation, turning the ring into a high-powered neodymium magnet. At this stage, the magnets are active and have very intense magnetic force. Operators must handle them with extreme caution, as their attraction can cause injury or damage electronic tools if not handled properly. Neodymium magnets are highly susceptible to corrosion, especially from moisture. To protect them, a nickel coating is applied. Each batch of magnets undergoes rigorous testing, and only those that meet quality standards are approved for packaging. The finished magnets are packed in protective boxes that shield them from external fields and prevent accidents caused by magnetic attraction. Like the video if you enjoyed it and share it with someone who might be interested. Also, subscribe to this channel and turn on notifications to keep learning. Thank you.